life sciences in Lublin. My presentation is based on the results obtained together with Maciej Haro, and the topic is from the field of classical geometric theorem analytic functions. So we consider the following subclasses of the class of all analytic functions in a unit disk D. H is the class of all functions f such that here we've got this normalization, usual normalization. S is the class of all univalent functions belonging to H. TL is the class of all typically real functions f in the that are functions that satisfy the condition signum of imaginaries of f of z is equal to signum of the imaginary part of z, whatever z in there. Yes, well, derjenigen is the signum function. One of the properties of this TL function is that they are symmetrical with respect to the real line. So everything I will be talking here will take place in the upper half of the complex domain. Here are graphic objects. It's rather two slides of graphic objects notation. I put them here only because I wanted to have everything formally okay, but I will skip these two slides and show you everything on the feature. So we have this main theorem, term 1, as a geometric condition that have f belonging to TR, and if for every z from the upper semi-unit disk, L plus of z belongs to, is a subset of f of d plus modulus z. Of course, then f is univalent. Of course, here this d plus modulus z is a semi-disk of radius modulus z through the function f, of course. And L plus I will show this. So here we've got our feature, and in the domain we have T plus is a semi-unit disk, a semi-unit circle. T plus modulus W is a semicircle which contains a point W, and this is all we have in the domain. And in the image we have f of t plus. This is the image of t plus through the function f of t plus modulus w. This arc, and we have here f of w, and here we've got semicircle which contains f of w, has the center in on the real line, and is tangent to the imaginary line. And we are interested in arc L plus of w. This is the arc which is a subset of t plus of f of w. And it joins the origin with the point f of w. And here we've got this arc is a subset of f of d plus. Here we would have d plus modulus w, since this would be this area between real line and this image of f of t plus modulus. So this arc is a subset of this disk function f. But of course, we have to check every such arc for every z belonging to t plus. And if the answer is positive, then f is I only mentioned that to prove our theorem we used this lemma that if for every z from the d plus L plus z belongs to the f of d plus modulus z, so we have the same assumption. We have that f of d plus L is a sum of these arcs for every radius n from 0. Okay, so now we can rewrite our geometric condition as an analytic condition. We have this equivalence. So here we have this geometric condition, and it is equivalent to this analytic condition. And of course, in this situation, we can say that theorem 1 and theorem 3 describe the subclass of the class S of all equivalent functions, of all functions f belonging to the R, satisfying an analytic condition, which I showed before. And furthermore, these functions are equally characterized by a geometric condition. This condition will act. Hence, one can say that the described functions form a new family of functions. We denote this family by SC. What I can say about this analytic condition is that one of our reviewers said it's a beautiful condition. Unfortunately, I cannot agree with that because here we've got z to the power 1 and f to the power 2. And because these these functions f are normalized such that the Taylor series start from z.
Excuse me, you need to share a presentation by Zoom.
So, because function f, its Taylor series starts from z, so if we had here the same power, so f would be squared and z would be squared, then we would be able to transform this condition such a way that we would have a real part greater than 0. And this mu transformed expression would be a formula of the function with positive real part. And then we would have more theorem for such functions with a positive real part. More theorem, more examples. It would be easier to create functions from our family. But nevertheless, this condition is quite nice because it's a short condition. It's a basic positive and basic advantage. Okay, and we decided to call these functions. We decided to call this graph because also we have this geometric condition. And what I would like to show you further is that some interesting function belongs to this class, this family. So we have here the Koebe function, and we can verify our analytic condition. And as you can see, everything is okay. So the Koebe function belongs to our family. And as you know, the Koebe function is quite important because this is the extremal function for many problems in the geometric theorem of univalent functions. And one of such problem is an example is the Koebe quantum theorem, where for every function, univalent function f, we have the unit disk d of radius 1/4 is a subset of the image of the unit disk through every univalent function f. And moreover, the Koebe function is the external for this inclusion. And you can of course you can consider similar problems as here. For example, not taking S but some subclass of S. And for example, you can consider the problem similar to the Koebe's one-part theorem for polynomials of each degree separately. And in this too is a paper by Dimitrievich and others. And they are introduced a special subclass of typical polynomials which can be which are extremal. And what I will show you next is that the following examples shows that P2, P3, and P4. So these polynomials of order 2, 3, and 4 respectively belong to our class C. These are only sketches of proofs. So P2 is given by this formula. We count this imaginary part of this expression. Here we got this minus. Here we got something which is obviously positive. This is also positive, so hence this imaginary part of this expression is less than 0, and P2 belongs to our class C. In a similar way, we prove that P3 and P4 belong to our class. I only put here sketches of proofs to show you one thing. First of all, we didn't come up with any sophisticated way to show that these polynomials belong to our class. We just determine it through apply directly our analytic conditions, checking this analytic condition. So as you can see, the greater the order of polynomial, the harder is to prove that this expression is this expression here is positive. Here we have this minus, which makes that the whole is negative, and here we've got polynomial for x from x is from the interval from -1 to 1, and this polynomials which we obtain have coefficients, positive coefficients, so this is obvious that for x from 0 to 1, this is positive, but for x from -1 to 0, it's not that obvious. And as I said, we didn't come up with any sophisticated way to show that it's belongs to our class. But computer simulations suggest that all such external polynomials are in our class, and I think it will be a nice result, because then in our class we would have the Koebe function, which is the general extremal function for classes, and have this extremal polynomials also in this class, and I think it will be a nice result. So all these extremal functions would have this property that you can go to the other point through the circle arc, which is inside the image of properties. Thank you for attention. References here. Thank you for attention.
Some question for Lens?
I just have a silly question about the condition that it's really neither compact, but have you tried to expand using this imaginary part of the product? Because if you split the condition in like z divided by f of z and the derivative divided by f, they look like really nice things. What is the logarithm part, or things like how it behaves as, let's call it like the ratio to the function and the value of z. So it could be nice to split that condition into simple. Okay, now here is the part of its predominant, so
I haven't thought about it, but I will. Why not? I will check it.
Maybe a short question, because you consider the subclass of typically real functions, and of course we have a lot of other subclasses of the S class, right? Thousands of subclasses, in fact. So it would be interesting. What is the correlation between your classes and the other classes, right? So it's clear that your class is a subclass of typical real function by definition. But how about the comparison of your class with complex functions, star-like functions, spiral-like functions, and so on and so on? I know that there are thousands of those classes, subclasses, right? So
I also
think
haven't
it would be
thought.
interesting.
Yes. I also haven't thought about it because with Maciej we started to try to generalize the condition. So we this is the area we are consider now. But yes, it's also very interesting how what is the relation with other classes.
Geometric characterization of class. The first or second theorem is very interesting. Could you please recall what is L plus? Once more.
Yes, once more. So in the image we have f of w, and we have the circle R, which join the origin with this f of w point. So so if we draw a circle here, it would be a circle which is a tangent to the imaginary line.
Yes.
Its center is on the real line, and it contains, of course, f of w. And this L plus z, or here L plus w, is the arc that joins